Hello, and welcome to this definitive explainer on loudspeaker technology. I invite you to go ahead and settle in, take a nice deep breath, and get your notes ready. We're going to take a very slow, measured, and highly academic journey today, exploring the foundational physics and engineering of acoustic transduction. Okay, let's begin. Here is exactly how we'll structure today's review. First, an introduction to loudspeakers. Second, the core features of loudspeakers. Third, moving coil loudspeakers. Fourth, electrodynamic loudspeakers. Fifth, horn loudspeakers. And finally, Section 6, loudspeakers for high-fidelity systems. We'll be moving deliberately through these 6 strict segments.
Okay, let's dive into this, starting with Section 1, our introduction to loudspeakers. I'd like you to carefully record this exact textbook definition: loudspeaker transduction. It is an essential component of all audio systems that converts electrical audio frequency signals into sound waves of the same frequency. Take just a moment to make sure you have that fully written down.
Now consider the really beautiful symmetry we find in electronics here. Thus, its work is opposite to that of a microphone. While a microphone captures physical sound pressure and turns it into an electrical signal, the loudspeaker takes that electrical signal and gently breathes sound back into the physical world. They are just perfect, elegant, mechanical mirrors of one another.
Moving on to Section 2, the universal features of loudspeakers. And this brilliantly illustrates the 6 core features you absolutely need to master for any engineering exam. Let's group them conceptually to make it easier to digest. First, the basics of output. Sensitivity is the input signal required for a sound pressure of 0.1 pascals at exactly 1 meter. Frequency response is the range of frequencies maintaining an amplitude of plus or minus 1 decibel. Next, we measure signal purity. Signal-to-noise ratio literally compares the output with a signal versus the output without one. And distortion, well, that manifests as nonlinearity in amplitude, frequency, or phase. Finally, we have spatial and electrical matching. Directivity is the ratio of maximum response compared to a standard omnidirectional baseline, and input impedance must strictly equal the source impedance to achieve maximum power transfer. Take a slow, careful look, and let this matrix really sink in.
Section 3, moving coil loudspeakers. Pay very close attention to the structural details here.
Let's read the precise working principle together. It operates just like a motor. Electric current in the voice coil interacts with a permanent magnet's field, causing a force that moves the coil and its attached conical diaphragm to produce sound. I'll give you a few seconds to let those mechanical principles truly absorb. If we examine the architectural cross-section carefully, notice the specific structural anchors. We have the permanent magnet, which is typically forged from a highly retentive alloy called Almaco. Observe the exact placement of the voice coil, suspended perfectly within that specific air gap. When current flows, the interaction between the permanent magnetic field and the induced field forces the coil and the attached paper cone to vibrate in physical space. Now, what's really interesting about this slide is how physical mechanics translate directly into an equivalent electrical circuit. It's honestly like a mathematical puzzle fitting together. L, C, and RC represent the basic electrical inductance and resistance of the voice coil. But if you look closely at the variables L, M, and Cm, the mechanical mass of the moving physical system is perfectly represented as electrical inductance, Lm, and the mechanical stiffness or compliance is represented as capacitance, Cm.
For your exams, you absolutely must memorize these high-yield technical metrics. The efficiency of the moving coil is notably poor. Only 5 to 10% of the signal power is actually converted into sound. That means up to 95% is just lost. The signal-to-noise ratio is approximately 30 decibels. It offers a wonderfully flat frequency response from 200 Hz to 5,000 Hz, and it's naturally omnidirectional. Because of these specific parameters, namely the low cost and that flat mid-range response, this is the exact hardware you've probably interacted with in everyday consumer electronics, like radio receivers, TV sets, or older cassette players.
Let's cleanly contrast the engineering reality here. The advantages of the moving coil are quite clear. It features a small physical size, extremely low production cost, and a highly satisfactory frequency response for general spoken audio. However, the disadvantages are structural. As we just saw, it suffers from very poor acoustic efficiency, and it noticeably attenuates or weakens both very low and very high audio frequencies. Moving systematically to Section 4, electrodynamic loudspeakers. Here is the defining textbook difference. The principle is essentially identical to the moving coil, but it replaces the permanent magnet with an electromagnet. A field coil wound over a central limb produces a very strong magnetic field. Think about that distinction for a moment. Because we have replaced that permanent magnet, the features change dramatically. This hardware strictly requires an external DC power supply to energize the electromagnet. Consequently, it can handle significantly more input power. Because of that incredibly strong induced magnetic field, power ratings for these specific speakers typically range from 25 watts all the way up to 100 watts. So the crucial point is understanding the engineering trade-off. The primary advantage is its robust ability to handle much more input power without failing. But the strict disadvantages are its increased cost compared to standard permanent magnet types and the absolute unwavering requirement of an external DC power supply just to maintain the magnetic field. It's a bit more complex. Section 5. Horn loudspeakers. Prepare to conceptualize a speaker that lacks a traditional cone. Please record this precise working principle. A horn loudspeaker does not deliver sound directly to open space. Instead, it acts as an acoustic transformer, delivering sound power to air trapped at the throat of a horn, which then radiates it outwards to the mouth. This concept of the acoustic transformer is absolutely vital. Visualize the strict architectural steps of its construction with me. Step 1. It starts with the familiar magnet, voice coil, and diaphragm, but deliberately without a cone. Step 2. It attaches a rigid horn that gradually expands from a small, highly constrained throat out to a large, wide mouth. And step 3, the engineering utilizes highly specific mathematical shapes for this rigid expansion, primarily canonical, exponential, or hyperbolic geometries. Let's move to and see how this builds into quite spectacular performance metrics. Because it acts as an acoustic transformer, perfectly matching the impedance of the voice coil to the air, the efficiency absolutely skyrockets to approximately 40%. The signal-to-noise ratio is a pristine 40 decibels, with a vast, flat response from 25 to 10,000 hertz. Interestingly, directivity behaves differently depending on the sound itself. It's omnidirectional at low frequencies, but forms a narrow, highly concentrated cone at high frequencies. Due to their immense efficiency, they are almost exclusively used in public address systems and massive auditoriums. We must contrast its parameters carefully for your exams. The advantages are immense: incredibly high efficiency, excellent power handling capacity, and vastly superior acoustical impedance matching. The disadvantages, however, heavily restrict its everyday use. It requires a massive physical footprint, sometimes expanding up to a full 2 meters in length, and it is significantly more complex and costly to manufacture. And finally, Section 6, loudspeakers for high-fidelity systems. Please copy down this final, precise textbook definition. A high-fidelity system utilizes a specialized acoustic enclosure that brilliantly combines a cone loudspeaker with an exponential horn to maximize audio reproduction quality. Just take a few seconds to let that sink in. As we gently conclude today's explainer, I want to leave you with a conceptual challenge for your exams. In high-fidelity systems, the physical cone actually faces away from the audience, redirecting the output solely through the exponential horn. So, how might this inverse structural layout fundamentally alter the physics of distortion in our ongoing pursuit of perfect sound? Take your time, reflect deeply on all the beautiful mechanical interactions we've covered today, and keep studying.